Hello, welcome back. In this segment, I will prove this proposition. Let us assume a number a can be written as p1 power a1, p2 power a2, and so on, pn power an. What are the divisors of a? We can argue that the divisors of a must be of the form p1 power d1, p2 power d2, pn power dn. So these are the divisors of a. For all d's that are lying between 0 and ai, where I is from 1 to n. Essentially, although this looks a little scary with all the symbols, if you know the prime factors of a number, we can find out all the divisors of the number. Suppose I give you a prime factor of, say, 15, you can right away tell the divisors of 15 are 3, 5, 15, right? Those are the divisors of 15. So you can derive this easily from prime factors. Note that I put di to be 0. That means I mentioned to you earlier that you can just take the prime factors and ignore some prime factor. For example, let's say ignore pn, right? In that case, your dn will be 0, which is naturally correct because the rest of the d's, right, will divide the a's. Okay. So the proof is important now. We cannot just use examples to prove. We have to prove it generally. Okay, let's start with this assumption that di is less than ai. Di is less than or equal to ai. In that case, right, I can rewrite my a as follows. So I can just say a is equal to p1 power a1 minus d1, which is positive because or non-negative, strictly speaking, because di is less than or equal to ai. This means a1 minus d1 is greater than or equal to 0. And p2 times a2 minus d2, and so on, right? All the way until an minus dn. But then I need to make sure I compensate for all the things that I subtracted, right? Which means I need to multiply this by p1 power d1, right? When you multiply, you add the powers. So a1 minus d1 will be added with d1, which means you get a1. And p2 times d2 and so on, right? It's just rewriting this using exponent rule. Uh, that's basically it. Okay. Now, what is this? P1 power D1, P2 power D2, and so on is nothing but D. So I have A is equal to something. That's the something that you can rewrite here is just this expression times D, right? This whole thing is D, right? This whole thing is called D. Okay. So when you write A is equal to something times D, you can right away say D divides A. That is the definition of divides. Okay. So we found out that if the exponent power is right, less than or equal to corresponding exponent power, you have a divisor of A. That's the divisor D. Okay. So given the prime factors, right, we will be able to easily direct all divisors of that prime factor, all divisors of that number. Okay. All right. What about the other way around? Meaning we assume that D divides A. Now we will show that the D must have the property P1 power D1, P2 power D2, and so on. Let's do that now. Now I'm going the other way to show to you that if D divides A, D must have the form P1 power D1, P2 power D2, and so on, and Di is less than or equal to AI. If D divides A, what does it mean? It means A is equal to some B times D. right? That is a definition of D divides A. It's just a straightforward definition of divides. Whatever prime factors B has, whatever prime factors D has, that must be the prime factors of A also, right? Because A is written as product of B and D. Yeah, if you expand B into prime factors, okay, in case B is a composite number, you can expand that into a bunch of prime factors. And same for D, you will get a bunch of prime factors. Okay. Now think about the structure of those prime factors for B and D. They must be one of those prime numbers, right? Because we know that A is made of P1, P2, all the way until Pn. That means B, if you were to write B as product of primes and D as product of primes, you will be using these primes only. Okay, that means we could say B is made of P1 power some B1. By the way, B1 can be 0. That means you're not taking that particular prime number. That is the meaning. P2 power B2 and all the way, say, to Pn power Bn. Okay, some of the Bn's, Bi's can be 0 because we don't need that particular prime for the prime factors of B. Okay. Similarly, D must also be made of P1 power some D1, and D1 can be 0 very well. Any Di, in fact, can be 0. Okay. And P2 power D2 all the way until Pn power Dn. Okay. Now, what will happen if you do A times B times D? If you do B times D, okay, what is B times D? B times D means you multiply corresponding, you see P1 and you have P1. That means you'll be adding the powers. P1 power B1 plus D1 all the way until Pn power Bn plus Dn. Okay. Now, we do know A is nothing but B times D. And we do know A is made of P1 power A1, P2 power A2, and so on. But each power of A, each Pi power is made of Bn plus Di, Bn plus Dn. Okay. That means we could say AI is equal to, AI means the power. You see here, this is A1, A2. So one of the ith element is AI is made of Bi plus Di. But we know that Bi, Di are all greater than or equal to 0. That means AI is also greater than or equal to 0, which means AI is greater than or equal to Di for all I from 1 through n. Okay. What can we conclude now? What we can conclude, though, is that AI is greater than or equal to Di. That means if you take your A, which is made of primes P1 through Pn with powers A1 through An, and if you now take D, for example, right, which is made of P1 power D1, P2 power T2, Pn power Dn, we argued that if D divides A, we can conclude that D1 through Dn is bounded by A1 through An. That's exactly what we proved. You could similarly argue that A is also greater than or equal to Bi because Ba and Di are positive or non-negative. So AI is greater than or equal to Bi, which means the powers of the prime powers of A are greater than or equal to the prime powers of B. Okay. That's exactly what we concluded here, that all divisors, right? All divisors of A must have the same structure as the prime factors. But the only caveat is that some of the prime factors may not be needed. That's the reason why we are allowing Di to be 0. Okay. So given the prime factors of a number, we can detect all possible divisors using this proposition. All divisors of A include numbers from 0 through AI inclusive, and we allow the divisor's power to be 0. which means some of the primes are ignored, and all small numbers, di less than or equal to ai means you can select every power which is smaller than or equal to the power of pi. That becomes your d. Okay, so the proposition is proved now that given prime factors of a given number, we can easily list all the possible divisors of the number. Okay, that's all. Thank you very much for your attention.